Hello everyone, my name is Stu Adler. Welcome back to Introductory Lectures in Thermodynamics. In the last two episodes, we explored the use of chemical potentials to understand phase equilibria in ideal and non-ideal mixtures. This completed our discussion of the second of three examples I outlined in episode A1 at the beginning of the quarter. However, we have one remaining, the question of reaction equilibrium. Although we don't have time to explore this topic in complete depth, this is, after all, the last episode of the course, I do at least want to introduce you to some of the key ideas. In particular, it turns out we can apply the same basic ideas of chemical potential to understanding reaction equilibria in mixtures. After covering a few of the basics, let's come back to our working example of ammonia synthesis and try to predict reactor conversion versus temperature and pressure. So far, all the examples of equilibria we've explored have involved physical transformations of molecules. With a physical transformation, the molecules cannot appear or disappear. They can only change their state of aggregation, or move from one phase to another. The essential difference when we have a reaction, such as the one shown here, is that the molecules have an additional degree of freedom. As we proceed from left to right, nitrogen and hydrogen disappear from the gas mixture, while ammonia appears, in accordance with overall mass conservation and the stoichiometry of this reaction. So we have two essential challenges. The first is that we need to extend the concept of chemical potential to include this additional degree of freedom. That turns out to be the easy part. The other challenge, and the one that we need to think about in some depth, is how to handle the reference state for energy and entropy of nitrogen, hydrogen, and ammonia when the number of each of these molecules is not conserved. First, let's consider how to formulate our statement of equilibrium. Thinking more generally than the ammonia reaction, consider the general reaction statement shown here, where Ri and Pi are enumerated reactants and products, respectively, and νi are the stoichiometric coefficients for these molecules in the reaction, defined as positive. Imagine these reacting species coexist in a single-phase mixture at a fixed temperature and pressure, and are free to appear or disappear from the mixture in integer ratios given by these stoichiometric coefficients. What will happen to the Gibbs free energy? To make it clear what's happening, let's draw the region of space we're talking about, but depict the reactants and products separately, even though they overlap in physical space. Imagine we allow the reaction to proceed by a small amount, given by the differential extent of reaction, dxi. This will cause a differential decrease in the number of moles of each reactant given by νi times dxi, and likewise a differential increase in the number of moles of each product. As we did with phase equilibrium, we can write the total derivative of Gibbs free energy dg as a sum of dni times the partial molar Gibbs free energy of each species, including both the reactants and products. At equilibrium, we require dg dxi to be 0, in which case the sum of νi times g bar I of the reactants must equal the sum of νi times g bar I of the products. Once again identifying the partial molar Gibbs free energy as the chemical potential, we can likewise say that the sum of νi times μi of the reactants and products must be equal at equilibrium. As a quick example, consider a reaction you're probably familiar with from first-year chemistry: the dissociation of water into hydronium ions and hydroxide ions. Applying the relationship we just derived, we would say that 2 mu H2O must equal mu H3O plus mu OH minus. If we assume that both hydronium and hydroxide ions are very dilute, following the reasoning we used in episode C3, we can write the chemical potential of each of these species as mu0 plus RT log C over C0, where C0 is a reference concentration, often chosen in chemistry to be 1 molar, or 1 molal, which is 1 mole per kilogram of solvent. Meanwhile, consideration of the Gibbs-Duhem equation suggests that for vanishingly small concentrations of the ions, d mu H2O will approach 0, so mu H2O will be approximately constant, reflecting the fixed concentration and availability of H2O to react. Imposing equilibrium of the reactants and products, and then solving for concentration, we find the product of the ion concentrations will be equal to e to the minus delta G0 of reaction divided by RT, where delta G0 of reaction is defined as the difference in standard chemical potential of the products minus the reactants, times their respective stoichiometric coefficients. Based on the form of this equation, we can also identify the exponential as the equilibrium constant for the reaction. Rearranging, we can also say that delta G0 of reaction equals minus RT log K. The value of delta G0 for this reaction is tabulated as a function of temperature in many sources. At 25 degrees C, it is 79.9 kilojoules per mole. This is a positive number, implying the formation of the ions is unfavorable relative to water. So in pure water, we expect the concentration of these ions to be very small compared to H2O. Plugging in numbers, we get an equilibrium constant of 1.00 times 10 to the minus 14. If this is not looking familiar quite yet, let's take the base 10 logarithm of our equilibrium expression. You might now recognize these quantities as the pH and pOH, respectively, of the solution. For pH-neutral water, we have equal amounts of hydronium ions and hydroxide ions, so the pH is 7. Okay, so let's now turn to the gas phase reaction of hydrogen and nitrogen to form ammonia, and try to apply these same basic ideas. Based on the stoichiometry of the reaction, we expect that at equilibrium, mu N2 plus 3 mu H2 equals 2 mu NH3. For simplicity, let's assume that the gases behave as ideal gases, in which case we can express the chemical potential of each species as mu0 plus RT log of the partial pressure of that species divided by a reference pressure. Substituting and rearranging to isolate delta G0 of reaction, we get the expression shown here. Finally, rewriting in terms of mole fractions and total pressure, we get something similar to a solution reaction, where concentration is expressed as mole fraction, and the equilibrium is dependent on total pressure. As a working example, let's try to calculate the equilibrium constant and use this to predict the required equilibrium pressure for the reactor in episode A1 at a temperature of 600 Kelvin. Thus, to proceed, we need to determine delta G0 of reaction. As defined, delta G0 of reaction is the difference in standard chemical potential between reactants and products. But to remind you, these standard chemical potentials are just the Gibbs free energy of the gaseous species at temperature T and the reference pressure P0. These in turn are related to the enthalpy and entropy of those gases. So using hypothetical paths, we should be able to calculate these quantities just like we have been doing all quarter. However, here is where the second challenge I mentioned comes in. What reference state do we choose to define the enthalpy and entropy? With physical transformations, we usually pick a particular phase, temperature, and pressure for each molecule. That works because the only thing that can happen to those molecules is to change state of aggregation. But here molecules can appear and disappear, so we need to find a way to put the enthalpy and entropy of different molecules on a comparative basis. Usually the way this is done is to set the enthalpy and entropy of the elements comprising all the reacting molecules to 0 at a particular temperature and pressure, such as 25 degrees C in 1 atmosphere. Starting from this common reference point, we can then define the enthalpy and entropy of all molecules by adding formation of the molecules to our hypothetical path. Note that by element, we don't mean an atomic species, which would be difficult to measure properties for. We're talking about the natural state of the element, which for nitrogen and hydrogen is a diatomic gas. In this case, two of our reacting species, nitrogen and hydrogen, are elements under standard conditions. From this reference state, we need to construct a path to the reactant gases N2 and H2 at 1 atmosphere pressure and temperature T. This involves calculating delta H and delta S for a temperature change, which we already know how to do. Once we know H and S, we can then calculate G as H minus Ts. But what about ammonia? We need to calculate H and S of ammonia at temperature T and pressure P0. But our reference state is elements, nitrogen and hydrogen. So to get to the state of interest, we need to first make the molecule. If this formation is done at standard conditions of 25 degrees C and 1 atmosphere, chances are good that delta H and delta S have been tabulated. These are called the standard enthalpy of formation and standard entropy of formation, given in table A32 of our textbook for representative compounds. If a molecule is known, this quantity has probably been measured and is available somewhere. From here we can follow the same script as usual, heating to temperature T, calculating delta H and delta S for this leg, and then calculating G as H minus Ts. For many simple binary molecules such as ammonia, chances are good this calculation has already been done and thus G is tabulated as a function of temperature. Good sources include the JANF thermochemical tables and the Barron tables for binary compounds. Here, for example, is an excerpt from the Barron tables for NH3 gas. These numbers are all for a standard pressure of 1 atmosphere and are based on a reference state of elements at 25 C and 1 atmosphere. A number of values are tabulated as a function of temperature, including H, S, and G, and some others which I'll get back to in a moment. According to this table, at 1 atmosphere pressure and our example temperature of 600 Kelvin, the Gibbs free energy of ammonia gas is minus 166.125 kilojoules per mole. Likewise, looking up G at 600 Kelvin for nitrogen, we find a value of minus 118.412 kilojoules per mole. Note that I am retaining a lot of significant figures. This is because when we take the difference, we may end up with a small difference between large numbers, and we don't yet know how many digits to carry. Finally, for hydrogen, we find a value of minus 81.836 kilojoules per mole. Putting together, delta G0 of reaction is 31.7 kilojoules per mole after rounding the difference to 3 significant figures. Before moving on, I'd like to point out one additional feature of these tables and another often simpler way to calculate delta G0 of reaction. Returning to our hypothetical path, we could also imagine adopting a reference state of elements at temperature T rather than referencing T0. In this case, our reactants are already in their reference state at temperature T and pressure P0. Thus, we only need to calculate the formation of ammonia at temperature T. This quantity is usually called delta G0 of formation for the molecule at temperature T. Returning to delta G0 of reaction, we can always express G of each species at temperature T as the free energy of the elements comprising that molecule at temperature T, plus delta G0 of formation at that temperature. If we do this for every molecule, the elemental reference state drops out, and we just have a sum over delta G0 of formation for products minus reactants. Since H2 and N2 are elements, their delta G0 formation at any temperature is 0. This can be seen in the Barron tables, which also report delta G0 of formation. This leaves only the ammonia, which has a non-zero delta G0 formation. Plugging in and calculating, we get the same result. Delta G0 of reaction is 31.7 kilojoules per mole. Plugging this value into our expression for the equilibrium constant, we get a value of 1.74 times 10 to the minus 3 at 600 Kelvin. Okay, so onto the reactor. Recall from the practice quiz in week 1 that we fed a 3:1 ratio of hydrogen to nitrogen into a reactor with fractional conversion F. Performing a mass balance, we can express the outgoing moles from the reactor as a function of the incoming moles and the fractional conversion. Dividing each of these molar flow rates by the total molar flow rate in the stream gives us the mole fractions shown here for the 3 species as a function of F. Plugging into our equilibrium expression, we can solve for the required pressure as a function of fractional conversion. For F equals 0.20, we would need a pressure of about 10 atmospheres. As you can see, one advantage of using a database like the Barron tables is expediency, much like our use of the STEAM tables or the NIST webbook for single component properties. However, this advantage is predicated on knowing the temperature in advance. What happens if temperature is an unknown that we're solving for, or we need to do a repeating calculation, or we want to introduce T as a variable? For example, let's say we want to make a chart of pressure versus temperature and fractional conversion, like the one I showed you in episode A1. In this case, we need to integrate the hypothetical path that we worked out earlier ourselves. Let's start with nitrogen. It's an element, so adopting a reference date of 25 degrees C in 1 atmosphere, our hypothetical path only has one leg, heating from temperature T0 to T. As we've discussed, this involves integrating the ideal gas heat capacity at a constant pressure of 1 atmosphere. Looking up the correlation for Cp ideal gas in Appendix A22 of our text, we have three terms, A, B, and D. These can be readily integrated to obtain expressions for H and S of nitrogen. G of nitrogen is then given by H minus Ts. Note that in this calculation, I didn't calculate delta G for the leg itself. I calculated delta H and delta S and then calculated G at the end. This is because the differential integration of dg along a path is not something we've covered. You may learn more about that in Chem 326, but for now let's stick to what we already know how to do. For hydrogen, the path is the same, as is the correlation for Cp, so we can use the same expression we just derived for nitrogen, substituting different values of A, B, and D when we go to calculate for hydrogen. For ammonia, the story is similar, but here we have two legs. First, we need to form NH3 from the elements at 25 degrees C in 1 atmosphere. We can look up the values of delta H0 and delta S0 of formation at 25 degrees C in table A32 of our textbook. Unfortunately, the table does not report delta S0 directly, but we can calculate it from delta H0 and delta G0, simply by recognizing that delta G0 formation is delta H0 formation minus T0 times delta S0 formation. Leg 2 is the same as the other gases, as is the three-term correlation for heat capacity. Calculating G minus Ts, we get the expression shown here. Note the additional terms arising from delta H and delta S0 of formation. This circled quantity is not delta G0 of formation at either T0 or T. Rather, it represents the part of H and Ts that arise from having non-zero H and S at the reference temperature and pressure due to the reaction. Returning to delta G0 of reaction and substituting the expressions we just derived for G of each species, we get the expression shown here, where the terms delta A, delta B, and delta D are the differences in A, B, and D between reactants and products. This is now in a form where we can use a spreadsheet to calculate delta G0 of reaction at whatever conditions we need. In particular, let's calculate the chart of P versus T and F from episode A1. I'll post the spreadsheet on the class website for anyone wishing to take a closer look. Here on the left is a data block containing the heat capacity coefficients for the three species, ammonia, N2, and hydrogen, as well as the stoichiometrically weighted difference between them. Here also is delta H0 and delta S0 of formation for ammonia at 25 C in joules per mole, as well as the ideal gas constant R. The expression for delta G0 of reaction I showed you can be broken down into delta H0 of reaction and delta S0 of reaction, which for accounting purposes I've calculated separately as functions of temperature from 300 Kelvin to 900 Kelvin. The sum is shown here. This includes a value of 31.8 kilojoules per mole at 600 Kelvin, close to the value we calculated previously using the Barron tables. Calculated here is the equilibrium constant. Using these values and the material balance we worked out earlier, we can calculate pressure as a function of temperature along the vertical axis of the table and fractional conversion along the horizontal axis. The result is the same chart we used in episode A1 to understand some of the process design decisions made by Haber and Bosch in developing a commercial process for producing ammonia. This plot shows that at 1 atmosphere pressure, high fractional conversion can only be achieved at a low temperature where the reactants are unable to reach equilibrium kinetically. If we add a catalyst and raise the temperature, we can get the molecules to react fast enough, but conversion is less than 10%. By also raising the pressure to 10 bar, we can get to 20 to 25% conversion. This conversion was high enough that Haber and Bosch could combine their reactor with a condenser to separate the ammonia and then recycle the hydrogen and nitrogen. This concludes our whirlwind tour of thermodynamics for the quarter. Hopefully you enjoyed the course and learned some useful tools to help you predict equilibria and analyze process energetics and efficiency. Stay tuned for Chemi 326, which digs more deeply into classical thermodynamics and its application for predicting properties and phase equilibria, in particular under non-ideal conditions, as well as Chemi 455, which extends the ideas we've discussed here to 2D interfaces, and Chemi 457, which delves more deeply into the molecular origins of thermodynamic behavior, as well as kinetic and transport properties. You may have noticed the lack of a cartoon in this episode. So how about we end on this one by Norzer and Powry. For much of the quarter, we've discussed the importance and usefulness of the second law for understanding the spontaneous behavior of molecules. But we are made of molecules. So does that mean the second law is actually the meaning of life? I'll let you think about that one. Thanks for being a great class.